Hi, towards Riemann hypothesis. Let me talk to a crash introduction of the Riemann hypothesis, the million-dollar problem today. The young scientists who are looking for some pocket money may benefit from this talk. To start with, let me let me start with the harmonic series 1 plus half plus 1/3 plus 1/4 plus 1/5 plus 1/6, which is summation 1 by n, and we know it goes to infinity. It doesn't converge. The fact that the harmonic series diverges was first proven in 14th century by Nicole Oresme, but this achievement fell into obscurity. Proofs were given in the 17th century by Pietro Mengoli, Joan Bernoulli, and Jacob Bernoulli. So the proof goes as follows. It's a simple proof by term comparison between two series. So I start with the harmonic series 1 half, 1/3, 1/4, and replace by another series which is smaller in term by term comparison. And we show that the smaller series diverges, so the harmonic series also diverges. So how do I construct such a series? I take 1 and replace 1 as it is, keep half as it is. For 1/3, I replace it by a smaller number, which is 1/4. 1/4 I keep as it is. From 1/5 to 1/8, I replace them by 1/8, which is smaller. Then from 1/9 to 1/16, the 8 entries I replace by the smaller entry 1/16. Now, so harmonic series is bigger than this series. Finally, how does this series look? So 1 comes here, half comes here, 1/4 plus 1/4 is half, 1/8 4 times is half, 1/16 8 times is another half. So 1 plus half plus half plus half, and it continues like that, and we know this goes to infinity. So this is a simple proof of the divergence of harmonic series. It diverges slowly at the rate of log n. Now there comes a problem, which is Bessel problem, which is the next possible study. So I look at the instead of looking summation 1 by n, I look at the summation 1 by n square, 1 plus 1/4 plus 1/9 plus 1/16, and Euler proves that this equal to pi square by 6. I don't know how pi comes up. Believe it or not, the sum goes to pi square by 6. This is known as Bessel problem because the problem is named after Bessel, hometown of Euler, as well as of Bernoulli family, who unsuccessfully attacked the problem. So this name Bessel problem comes from a place the hometown of Euler and Bernoulli family. So let us look at Euler's proof. So we start with the sine series, x minus x cubed by 3 factorial plus x5 by factorial minus x7 by 7 factorial. So if I look at sin x by x, it is 1 minus x squared by 3 factorial plus x4 by 4 factorial minus x6 by 7 factorial. Now this is a power series having only the even powers of x. Now we know from the from Gauss's derivation that any polynomial can be written as the product of x minus ai, where ai's are the roots. But Euler applied the same concept here for a power series, and he writes sin x by x as 1 minus x by pi plus 1 into 1 plus x by pi into 1 minus x minus 2 pi, 1 minus x by 2 pi into 1 plus x by 2 pi, because the zeros are pi, plus pi, minus pi, plus minus 2 pi, plus minus 3 pi, etc. At the time when Euler published this proof, it was not rigorized. It was rigorized later by Weierstrass, and it is known as Weierstrass factorization theorem. Then you can do such things for the power series also. and it came after 100 years when Euler published this proof. But Euler was so confident by his numerical calculation of the partial sums that he boldly put this as a decomposition of sin x by x. Now, if you look at the final series, it is 1 minus x square by pi square into 1 minus x square by 4 pi square into 1 minus x square by 9 pi square. So if you calculate, if you take out the coefficient of x square, you get this identity summation 1 by n square equal to pi square by 6. And if you look at summation 1 by n to the power 4, using the coefficients of equating the coefficients of x power 4, it is pi 4 by 90, summation 1 by n to the power 2, it is pi to the power 8 by 9490, and so on. So this is known as Bessel problem. So it is obvious to look at the function zs as Euler defined it, summation 1 n equal to 1 to infinity 1 to the power s. Now certainly for s equal to 1, this is a harmonic series and it diverges, but for s bigger than 1, this series converges. I haven't got the proof, so I'm omitting the proof here. Now, next step is Euler connects the primes to Zs, and he proved such a formula that summation n equal to 1 to infinity n to the power s equal to product over all primes 1 minus prime to the power minus s whole inverse, and this holds for all s bigger than 1. There are proofs of it using the series 1 by 1 minus x equal to 1 plus x square plus x cube for mod x less than 1. So we can write 1 minus 1 by 1 minus 1 by p to the power s as a sum. Then I have the product over all primes, and if we interchange sum and product, we get sum over all k tuples and product over all primes 1 by p power k1s, p power k2s, pt power kts. But these are not by the factorization of the natural numbers from Gauss's theorem of unique factorization theorem. We can say that product over all primes 1 minus prime to the power minus whole to the power minus is nothing but sum over 1 by n power s in ranging over the all natural numbers. Now, an alternative proof can be given using the idea of C of Eratosthenes. That is, if you start with a natural number, say 2 to say set of natural numbers, say 2 to n, first keep 2 and remove all the composites which are multiple of 2. Then next number is 3, so keep 3 and remove all the multiples of 3 which are composite. This way, if you iterate this operation for root n times, you remove all the composite numbers from the set 2 to capital N, and what remains are prime. So this is called C of Eratosthenes, and this idea can be used here. So we start with Z is equal to 1 by 1 plus 1 by 2 power s plus 1 by 3 power s plus 1 by 4 power s, and you multiply by 1 minus 1 by 2 power s and into Zs. So this is Zs minus 2 power minus into Zs. So all the multiples of 2 get cancelled, and what remains is the other terms. Now you multiply by 1 minus 3 power minus s, and all the multiples of 3 are gone now. Similarly, if all the multiples of primes are gone now, when I take the product over all prime 1 minus prime to the power minus s into zs, it is 1. So z is equal to product over p prime 1 minus p to the power minus s minus 1. So this is simple proof of which they call the golden key, summation 1 by s equal to product over 1 minus p to the power minus s to the power minus 1. Now, Riemann started to look into this function, and he extends Zs to larger domain. First, Riemann changed the symbol to Zs to zeta s when he extends it to complex plane. So let us look at some domain stretching. So we know zeta s, I call it now, to be defined on s bigger than 1. Now, if we consider the function eta s 1 by 1 minus 2 to the power s plus 1 by 3 to the power s minus 1 minus 3 to the power s plus 1 by 5 to the power s, and it is convergent. I haven't got the proof yet, it is convergent for s bigger than 0, but zeta s can be written in the form of eta s. Zeta s equal to 1 minus 2 to the power 1 minus s whole inverse into eta s. Now if we extend zeta s with this form, it is convergent for s bigger than 0. Now now the Riemann zeta function can be extended negative also using this formula that Euler suggested in 1749 and finally proved by Riemann in his 1859 paper, that zeta of 1 minus s is 2 power 1 minus s pi power minus s sine of 1 minus s by 2 pi s minus 1 factorial zeta s. So it's the relation between 1 minus s and zeta s, and you can get the negative for negative values of s, you get a well-defined value for zeta s. For non-integer value of s, you can approximate s minus 1 factorial by gamma function. Now, in this form, if you take the argument as minus 2n, that is the negative integer values, then sine of 1 minus s by 2 pi becomes minus n pi and is 0. So zeta s is 0 for in minus 2n for n bigger than 1. These are called trivial zeros. Now another form Riemann used to extend it to analytical to whole of complex plane is like this. And now if we look at the non-trivial zeros of zeta, we get such values that half plus some real number into I, take the zeta, it is 0. So these are some zeros of zeta which are on the x is equal to half line. And Hardy in 1914 get the result that zeta s has many zeros with real part half. So has infinitely many zeros. So there are infinitely many zeros is on the s equal to real part of s equal to half line. And Riemann hypothesis says whenever zeta is equal to 0, it has to be the real part of the argument. If it is a non-trivial 0, has to be half plus some I into t. So this is the Riemann hypothesis, and an equivalence, interesting equivalence we can note down. If px denotes the number of primes up to x, px is like x by log x. It's a good estimate. A better estimate by Gauss is px is approximately Lix, where Lix is defined as integral 2 to infinity dt by log t. Now it's a fact that even Riemann hypothesis is true, px never differs from Lix by more than root x log x. Okay, but the converse is also true. If px never differs from Lix by more than root x log x, then Riemann hypothesis is true. There are some references. I stop here, but I haven't talked about the connection of Riemann hypothesis with quantum mechanics, the Hermitian operators. Those are the uh, quite new subjects, and because of these interconnections, Riemann hypothesis is very much of importance as an unsolved problem in mathematics till today, and it has got a lot of applications. People are really trying hard to prove Riemann hypothesis, because we have got trillion zeros of zeta s which are on the real part of s equal to half line, and the Riemann hypothesis we feel is very much true, but the proof is not still available. Mainly, I got the stuff from the book Prime Obsession by Bernhard Riemann, Prime Obsession, Bernhard Riemann, and Greatest Unsolved Problem in Mathematics. PDF is available freely in the net. If you want, you can have a look. Thank you.